Welcome to today's class on functional analysis. We now prove some useful results about continuous linear extensions and about convergence of continuous linear maps when the range space is a Banach space. So we state a theorem 8.3. Let X be a normed space and Y be a Banach space. A. Let X naught be a dense subspace of X and F naught belongs to BL of X Y naught. Then there is a unique F belongs to BL of XY such that F restricted to X naught equal to F naught. Also norm F equal to norm F naught. Now we prove this theorem. Let X naught be a dense subspace of X and let F naught belongs to BL of X naught Y. Let X belongs to X. Then there is a sequence Xn in X naught such that Xn converges to X. This is because X naught is dense in X and X belongs to X. Now since norm of F naught of Xn minus F naught of Xm is less than or equal to norm F naught into norm Xn minus Xm for all n, m equal to 1, 2, etc. We see that the sequence F naught of Xn is a Cauchy sequence in Y. And since Y is a Banach space, F naught of Xn converges to some Y in Y. Define F of X equal to Y. Then F from X to Y is well defined and continuous, and norm of F equal to norm of F naught. Since for all X in X, norm of F of X, this is equal to limit n tends to infinity norm of F of Xn. So this is a limit n tends to infinity norm of F restricted to X naught of Xn, and this is less than or equal to norm of F restricted to X naught into limit n tends to infinity norm of Xn. So this is equal to norm of F naught into norm X. And the uniqueness of F follows from the denseness of X naught in X. Remember that a sequence cannot have more than one limit. So the Y is unique, so F must be unique. So this proves part A. Now we prove theorem 8.3b. Let X be a normed space and Y be a Banach space. Consider Fn belongs to BL of XY such that norm Fn is less than or equal to alpha for all n and some alpha greater than 0. Let E be a subset of X whose span is dense in X assume that fn of x converges in y for every x in E. Then there is a unique f in BL of xy such that fn of x converges to fx in y for every x in x. Proof. Let x naught be the span of E. Since fn belongs to BL of xy, fn is linear. And since fn of x converges for every x in E, fn of x converges for every x in x naught. This is because x naught is the span of E. For x in x naught, let f naught of x equal to limit n tends to infinity fn of x. So that norm of f naught of x equal to limit n tends to infinity norm of fn of x. This is less than or equal to alpha times norm x. Since norm fn is less than or equal to alpha for all n. This shows that f naught belongs to BL of x naught y. Therefore, by A of this theorem, by part A, there is a unique f in BL of xy such that f restricted to x naught is f naught. So we have proved the existence of an f in BL of xy. Now we are going to show that fn of x converges to f of x for every x in x, for which let x belongs to x and epsilon positive. Find x naught in x naught such that norm of x minus x naught less than epsilon and a positive integer n naught such that norm of fn of x naught minus f of x naught is less than epsilon for all n greater than or equal to n naught. This is since fn of x converges to f naught of x for all x in x naught. So such choices are possible. So now we are going to show that fn of x converges to f of x for x in x. Now you consider norm fn of x minus f of x. This is equal to norm of fn of x minus fn of x naught plus fn of x naught minus f of x naught plus f of x naught minus f of x. So this is equal to norm of fn of x minus x naught plus fn minus f of x naught plus f of x naught minus x. So this is less than or equal to norm of Fn of x minus x naught plus norm of Fn minus f of x naught plus norm of f of x naught minus x. So this is less than or equal to norm Fn into norm x minus x naught plus norm of Fn of x minus Fn of x naught minus f of x naught plus norm f into norm x naught minus x. So this is equal to norm of Fn plus norm f into norm of x minus x naught plus norm Fn of x naught minus f of x naught. You know that Fn is less than or equal to alpha, so this is less than or equal to alpha plus norm f into, norm of x minus x naught is less than or equal to epsilon plus, and you also have norm of Fn of x naught minus f of x naught is less than or equal to epsilon, so this is plus epsilon. So this implies norm of Fn of x minus f of x less than or equal to alpha plus norm f plus 1 into epsilon. This is true for all n greater than or equal to n naught. So this shows that Fn of x converges to f of x for every x in x. So this proves the theorem. That's all for today.